So any particular nerve could have a number of stimuli on it at any one time. One nerve will connect to lots of different nerves. Does every single stimulus always cause an action potential? Does every little depolarization on a cell cause an action potential down the axon? No, it doesn't. Just like we know, every little insult doesn't make us come out really angry. But we have a threshold. If somebody continues to wind us up the wrong way, then, we'll reach a limit and we'll go, now, you can't treat me like that. And that's what nerve cells do. They reach a threshold, and at that point, the action potential will fire down the axon. And what will happen? The membrane will get depolarized by about 15 to 20 millivolts, so it's not a huge depolarization that's going to set this off. But when you do reach that depolarization, then the voltage itself will be enough to trigger the opening of the sodium channels. So we have sodium ion channels that open because of a stimulus such as a neurotransmitter, and we have others that will open because of stretch, or we have them that will open because there is a depolarization, a small depolarization. And along the axon, they open because of depolarization. So once we get a depolarization of this amount, that's enough to start opening the sodium channels. The sodium, it will then enter the cell in the channel, and now we've got a positive feedback mechanism, because sodium entering the cell causes depolarization, and the depolarization will open the sodium channels. So now we've got depolarization opening sodium channels, causing more depolarization, opening more sodium channels, causing more depolarization, opening more sodium channels. And that is why our action potential will fire. But it has to reach this threshold before that positive feedback will start. This positive feedback is on the cellular level within one cell. This isn't a whole body positive feedback. So this is why I didn't talk about it in homeostasis, because although this is a positive feedback cycle, this is a positive feedback cycle on a cellular level, not on an organismal level. Now, when the action potential fires, it's called an all or none phenomenon. So what does that mean? Well, if we reach threshold at the start of the axon, then an action potential is sent down the axon because of this positive feedback mechanism. So either there is an action potential or there is not. It's an all or nothing binary phenomenon. Yes or no. There's not a little action potential or a big action potential. No. Which then begs the question, how does one nerve tell another nerve, or tell a muscle, or tell a gland that this is a big response that's required? We need more. This is important. If the action potential can only do this, how can it give a message of saying more? And the way it does it is by sending more action potentials. It's if everyone is the same, which is how does you tell one action potential? How does one action potential differ from another? They don't. Every action potential is the same. So how can the central nervous system differentiate between a weak stimulus or a strong one? You just send more of them. Weak stimulus, strong stimulus. Okay? So if you've got a 2-year-old child standing on your toes, your brain gets a slow clap from those pressure sensors. If you've got a truck rolling over your foot, you're getting many, many action potentials firing very quickly. And here's what we're that's trying to draw a picture to show this. If we do not, this is the threshold stimulus, so we're looking at stimulus voltage. If we get a voltage stimulus that doesn't hit threshold, we're not going to get an action potential firing. That's not enough. You know, you don't, a feather landing on my foot, I might not even feel it. A baby treading on my foot, okay, a few action potentials are going to fire. An elephant standing on my foot or a truck rolling over my foot, okay, masses of action potentials would fire down that nerve. Now, if we remember the picture that we looked at before of the action potential, the depolarization rising, the repolarization, and then the hyperpolarization, we're going to see that there are times when you will not be able to open those channels again. So we have an absolute refractory period where it's not possible to start another impulse, to start another action potential. When the channels are already open and the sodium is going into the cell, that's an absolute refractory period. We can't get more of a response than we're already getting at that point. A second stimulus can't do anything. So the stimulus hits here. Oh, didn't mean to do that. The stimulus is going to hit here, and it wouldn't matter how many more stimuli I put in this. It doesn't matter how many more elephants trod on my foot. I couldn't send another message in that time. But if I, let's get rid of those. If I had a stimulus after this, in this area, this is a relative refractory period. So we've now closed our sodium channels. They could reopen, but as the potassium is leaving the cell, I'm going to need a bigger stimulus to be able to make a difference, to reach threshold again. Because I've got all my potassium leaving the cell, so the sodium that's got to enter the cell has got to counteract the potassium leaving and try and push a depolarization at the same time. So it's a relative refractory period. If that truck goes over my foot, yes, I would be able to trigger another depolarization. But if it's a feather, that's not going to be able to do enough to get me to trigger another action potential coming. So writing that down, following a relative refractory period follows the absolute refractory period. Most of the sodium channels have returned to their resting state, but some of the potassium channels are still open. Therefore, the threshold for the action potential generation is elevated because we have to counteract the potassium effects as well as depolarize. So only an exceptionally strong stimulus could stimulate an action potential. Yeah, and I've explained that, I think. So now we'll come back to another video to look at the synapse.